Hello. I don't know if folks can hear this over Zoom, but our campus on Idaho Falls, I think it's a debate team from Salt Lake that came down, so it's pretty busy here. Okay, well, welcome back, everyone. Looks like it's time to get started. Again, it's kind of loud here on the Idaho Falls campus, so I'll just try to do my best to tune it out. This room has pretty good soundproofing, so it's kind of amazing. I can actually hear them so well out of there, out in the hallway. But for what we're doing today, we're just moving through section 3.4 and potentially starting section 3.5 on nested quantifiers. Any questions at the moment, folks, before we get started with today's work? Okay, well, we left off defining what a predicate function is. And finally, we got to the universal and existential quantifiers, but we didn't have a chance to actually put them into play. We mostly talked about the analogy of the universal quantifier. If you have a finite set for the domain of discourse S, it's really going to be thought of as just being an overloaded or supersized, as our author calls it, and operator. So if you have a finite set, then the statement for all x and s, the predicate p of x is true, we just abbreviate to p of x, is just thought of this way. For the first element and for the second element and so on, we're saying the predicate at those elements comes out as true. For the existential quantifier, we'll be using this backwards E symbol as opposed to the upside down A symbol for the universal. We are just going to say there exists x and s such that p of x is true for at least one possible element x in S. But thinking in terms of what we've done before in logic, this is really just a whole string of OR operators. This is an analogy in the sense that it could break down if your domain of discourse is the set of real numbers. That's an infinite set, but it's even worse. I can't list out all the entries like I can on these two values or these two situations here. But still, it's a great way to think about what the universal quantifier for all and the existential quantifier there exists are really trying to say. So we'll work will be practicing working with these, determining if they are true or false, and we'll loop back into talking about the predicate function. Let me redo the highlighting here. We'll loop back into talking about the predicate function on each one of these problems as we go through the notes, just to get extra practice on working with predicates themselves. Okay, let's go with green just to emphasize. For our first example, we have the statement for all x in R, x squared minus 2 is greater than or equal to 0. So it's a statement much like this, but now our predicate function is the statement p of x. It's defined by x squared minus 2 is greater than or equal to 0. And we can say even more about that function p. P is mapping as a true function as we define them in the chapter 2. P maps from the set R to the set true false, the Boolean valued object here that we've been working with so far in chapter 3. So we just want to determine, is this true or false? Let's analyze it for a moment. X squared minus 2 greater than or equal to 0. You know, it looks pretty good unless we look at it really carefully. Can anyone see a value for x that could make it false? Yeah, absolutely. If you choose one particular value from the domain of discourse, R, I'll just often say domain, say 0 as you chose, we get a false statement. We can then say this is false. By this, we mean the entire quantified statement. This is a very powerful statement when you say for every single x that's a real number, you have that this is a non-negative quantity. That's false because at p at 0, we've exhibited one false output. And that's all you have to have for this entire thing to fall down and become totally a false statement. It goes back to this definition. This is going to be true if for every possible element in the domain, the predicate comes out as a true. So exhibiting one false element here, one element that outputs a false in the predicate function, tells us the whole statement is false altogether. Well, we did it, folks. That's our run on this one, part A. Any questions with this problem so far?
Could we find a way to modify that left side, the under or upside down AX to make this predicate true?
I believe you could. You could say, instead of having R there, you could flip that to say, how about, let's make it be something like square root of 2 off to infinity. If I pick this as my domain, then, well, the minimum value I put in is root 2. Root 2 squared minus 2 is 0, but that qualifies as a true statement. And any other larger real number I throw in there is going to make this true as well. So that's one way to do it, just change the domain. But there's a whole nother way. You could just negate this entire statement. If this statement's true, or excuse me, if this statement is false, as we determined, the negation of the entire statement will come out true. So that'd be a second way to do it. Does that make sense with that question there so far?
Yes. So could we put in like negative infinity comma negative root 2 union with root 2 comma infinity? Yeah.
Yeah, absolutely. That would have done the job as well. If you just say, take out all the elements where you have a problem, where the predicate became false, then you get it. This is an overall true statement. Because now every single value you pick in this refined domain of discourse, swapping out for ours, we can never get false. We'll always have true. Absolutely. And a third way, we said one way is negating it, but a whole third way to make this entire statement true is you could just take this thing right here, swap it for exists and x in the real numbers such that x squared minus 2 is greater than or equal to 0. Whole statement's true now because for the existential quantifier, the entire statement comes out as true if you find just one, at least one element that makes it true. So if this was existential and I pick, say, 5, 5 squared minus 2 is positive, and we get a true statement out. Other questions with that one so far? Okay, let's think in terms of negation though. I'm putting a little border here to say the problem is over. We said it's false. We showed why we have a false statement when we plug 0 inside there. Negative 2 is not greater than or equal to 0. But what if you did this? Take the entire original quantified statement and rewrite, let's put this in orange just to say it's a comment. Negation of, for all x in R, x squared minus 2 is greater than or equal to 0. We can, in fact, just negate that entire statement if we ever found that to be worthwhile. If we negated that statement, we borrow material that we saw in the prior section, 3.3, De Morgan's laws. Even though this is an uncountably infinite set, the analogy that we have here on having a bunch of ands does work for the existential, or excuse me, the universal quantifier.
I have a
We
question.
negate this whole statement. Yeah, go ahead.
Sorry to interrupt, but I've been having I don't know, it's just been difficult for me to understand the sign, like the three lines. I was wondering if you could explain it again.
Yeah, those 3 lines that you see there are a type of equality, but it's not exactly equality because these aren't real numbers. What it means is logical equivalence. So we had 3 lines right here on this example. What we were saying is the negation of P implies Q is logically equivalent to P and not Q. But then what that really means altogether is we go to this left side and then the right side across the triple lines, we have identical truth assignments. One side's false and so is the other. The other side's true and true, false to false, false to false. So logical equivalence really just says in a nutshell, let's look at this one right here, that if you're looking at negation of P and Q, it's the same thing, same exact truth assignments of not P or not Q. So it's a type of equality. It's essentially saying the left side is the same statement as the right side. Sure, it looks different with the logical connectives, but it's saying the same exact thing logically. Does that make sense with that question there?
Yes, thank you.
You bet. Thanks for asking about that. And that's one of the things that's kind of tricky about this is we have this huge table of logical equivalences, and we're about to use it in this statement right here. So we go up. Think of this universal quantifier as being essentially a whole bunch of and statements put together, even though this is an uncountably infinite set. If we negate something that involves and statements, which is effectively what this is saying, we can turn this into a different statement involving ors. So here's how it's going to work. But notice, if you have a whole bunch of ors, that's an existential quantified statement, not a universal any longer. So a couple of interesting things happen, and it's really through De Morgan's laws and this analogy down here. If you negate a universally quantified statement, it's going to give you a logically equivalent statement, the same exact truth assignments to there exists. So from all x, we say there exists one x in the same domain of discourse R, such that we also negate this part right here. The negation of x squared minus 2 is non-negative, would be the statement that x squared minus 2 is negative. So we take what was a greater than or equals, flip it to less than 0. So even though this problem is done here, this is still a kind of a useful thought. We're going to be negating these quantified statements. And because we had false here, the negation of something that is false tells us that this brand new statement here on the right is true. There really will exist some real number x such that this is negative. And you know, 0 would work. If you plug 0 inside here, 0 squared minus 2 is negative 2. So in fact, negative. So the original statement is saying for all x, non-negative, x squared minus 2, it's false. We can find a counterexample, plug in 0 into that predicate. But this one will, in fact, be true because we can make it be true for at least one possible x. That makes the whole overall statement true as we see it. Well, there's lots to put together, right? There's logical equivalences, there's predicate functions that are Boolean valued, and there's a quantifiers all at the same time. Any questions at the moment, folks? Just getting through this one. Okay, let's try it out again. It says determine if the following statement is true or false. So the answer to this, again, is going to be something like this, where our justification is work with the predicate valued function, or excuse me, the Boolean valued predicate function. Here, the predicate is going to be defined by P will output either true or false, depending on if x squared is in fact exactly 25. And this one's an existential quantifier. We can get a true statement on this if we find at least one value of x where this works out as true. But we can solve that equation. We get two solutions, right? -5 or +5. So there absolutely is values of x in the real number system that satisfies that equation. Now, it would be a problem, though, if we had, say, negative right there, right? We're avoiding the complex valued numbers, which was an issue and a topic that came up in chapter 2. But if there was a negative there, this would be a false statement outright. With positive there, yeah, we can solve this. We have two possible solutions. So we can say pretty briefly on this one, true, because If we take the predicate function, throw in the value, say 5 or -5 if you're feeling fancy, this comes out as true. And the whole statement is true if you can just find one value from the domain of discourse, outputting a true. Well, these problems go kind of quick, but it's a good time to spend some time on to just think about everything that happened on paper. Any questions with the solution in part B? Okay, and just because it's an important skill for us to practice, I'll put a border here to say the problem is over. You don't have to do this in the homework. Let's negate it just for the sake of practice. So if we take the entire negation of the statement that was true, we're expecting a false statement, and here's what it would look like. Negation of this entire exists x in R such that x squared equals 25 statement. Now notice the major thing that happens when we negate a quantified statement. Universal operator turns into an existential operator, and whatever you have here is the negation of what you have here when you go to this step. So if we go in the reverse direction, De Morgan's law supports us, we are going to get the statement is logically equivalent to a new statement for all x in R. We need to negate this. It's a lot different than negating an inequality symbol. If you have greater than or equal to 0, the negation is the strict inequality, strictly less than 0. If you're negating an equality, that one's not so bad. You just go x squared not equal, that makes sense for a negation, 25. But that's a powerful statement now, right? We went from there exists x to a statement for every x in R, x squared is not 25. That's got to be false, right? There's just no way that's true. We can find -5, +5 solves this. But we're also expecting false because we negated a statement that was originally true. So we can say down here, false. So that's quantified statements so far. Any questions, folks, on either A or B? Okay, one claim that I made that it's kind of fun to come back to on part C is we really have been working with quantified statements a lot. Not just in this class, we think in terms of quantified statements. All we're really doing is formalizing exactly and precisely what we mean when we use these quantifiers, the existential one and the universal one. And when we were way back in chapter 2 dealing with set theory, this was a quantified statement, the subset relationship. So if we want to be as extremely precise by what we mean, A is a subset equals B, we can quantify it, and that's what we'll do here in part C. First, let's go back to that chapter because it's been a while. I think I'm in the wrong spot. There we go. We're doing the subset equals relationship. Oftentimes I just say subset to refer to that one. The definition says A is a subset of B or equal to B if X is A. If for every X in A is a better way to say it, it is also an element of B. So let's throw that in. Notice the word for every. The big thing that to really pay attention to the notes is think in terms of for all, for every, really just being the universal quantifier. If we say there exists, or if we say for some, we're thinking in terms of the existential quantifier. But this one is a statement of every X in A. Here, there's a couple different solutions you can make. If I'm going to think of this being this entire set A is the domain of discourse. So much like in the last problems, R was the domain that we're working on. I'm going to think of A as the domain on this one because this definition didn't talk about a universal set U whatsoever. And we can just stay strictly in those lines and not introduce any universal set. Then the predicate on this one will be this entire statement here. It is also an element of B. So that's going to be the predicate statement, P of X altogether. So now when we go to write this out, we'll start here where it says for every. That's the universal quantifier. we'll say for every X in, we have to give it a domain or else it's not a properly entirely written out statement. But our domain is going to be elements of A. In the subset relationship, that's really all we care about. What elements do you have in A in the very first place? They have to also be an element of B. So we say for all elements X in A, the statement we quantify is X is an element of B. And that's the P of X statement right there. So it's a pretty fast, compact way of saying it. This entire statement here, original subset definition, can now, with all of our tools with logic, be way compressed down into this one quantified statement. But at its heart, it's not too different from what we were saying in these statements. We're just talking about subsets rather than real numbers and equations. Any questions at all, folks, making this translation from subsets down to quantifiers? Okay, this is kind of our first look at this type of work. We're also going to quantify the whole definition for a function in the very first place. But you know, that takes more than one quantifier. That's a tricky one because there's several sets we're working at the same time. We can also quantify one-to-one. We can quantify onto. So all those interesting definitions about functions, we can write in a very, very precise way now with our new tools and logic. Well, for the moment, this is the introduction to quantifiers, and we're going to kind of proceed similarly to what we did in 3.2, introducing predicates. We'll look at how to translate statements from the quantified language into ordinary language and then vice versa. And then we'll do a couple more problems like these just for the sake of extra practice. So here's our next challenge. Here are predicates, don't have anything to do with real numbers whatsoever. Looks like it's all about people this time. It says, define the predicates P of X, X is an ISU student, and the other predicate Q of X, X is a full-time student, and the domain of discourse on this one is going to be all living people. Living people here is just to be specific. I feel like it's weird to say all people, then it implies the question of, are you talking all past, present, or future people in that set? We're just saying everyone alive. So it says write each quantified statement in words. And this direction is not usually too bad. The tricky direction is to go backwards in this translation problem. So spend some extra time on that direction. The major thing to keep in mind, once again, is when you see this statement, this is shorthand for all, or you could say for every, if it just flows better in the sentence. And existential is going to be a shorthand for some, or you could say there exists, if that flows better. Let's say that down below, just to be specific. So with this information ready to go, the statement is now saying, for all X in S, that's for every living person, because that's what S is, all living people currently, P of X. That would be the person is an ISU student. It's definitely a weird claim, right? But for putting it down on paper, translating it literally as we see it, it's saying for every living person, that person is an ISU student. So when we said for every living person, we were talking about the domain of the problem. When we said that person is an ISU student, we were talking about the predicate functions, just P of X in this one. So that's kind of the name of the game so far. Any questions at the moment? Okay, I'm noticing this morning I found a typo in the notes. This is one of the things that's easy to kind of miss. I had it originally like this in the notes, but that's not a properly formed statement in the way our textbook introduces quantifiers. We want to always have the domain of discourse right inside there to be very, very specific. Other textbooks might take it off, and then there's an implied domain of discourse. But we're introducing this, so we want to be very precise with our language. And there was another typo I forgot. I didn't say what the domain of discourse was on example 5. So sorry for those typos, really just mistakes in the notes, I guess you could say. What I did was I went back to here, and I have the revised version for 3.4 if you want to pick up the corrected versions. Sorry for the distractions on those. But let's try this again. This one is an existential quantifier. It's talking about the domain of discourse S. But also we have a bigger compound statement. Really, it's just kind of 3.2 together with the quantifiers. We can say that this translates to there is some, I'll just say person, implied to be a living person. There's some person for which, the for which is kind of translating through the column. You could say such that instead if you prefer. We'll say for which they are an ISU student and negation of QFX, not a full-time student. So we'll say for which they are an ISU student and not Q of X, so not a full-time student. And that statement looks like that's absolutely true. There is non-full-time students that exist in ISU. This one was the one that looks like it's just obviously false. I mean, I know plenty of people who are not ISU students, and just finding one person who's a non-ISU student that's alive today is enough to show the whole statement was false. So for every is a very strong statement, but for there exists, this is true the moment you find just one part-time student who's enrolled in ISU. I'm sure there's quite a lot. Want any questions at all, folks, on either parts A or B? Okay, part C is not too different, except you could write out a whole statement that says every living person is a full-time student, and then maybe put in front of that statement, it's not the case that every living person is a full-time student. That's kind of awkward language, but that would be a totally acceptable answer, I'd say. Another way to go is, let's just negate the whole statement, practice that skill once again, because that statement would flow a lot better. So we could say this whole thing is logically equivalent. It's the same exact statement as flip the existential quantifier for all to the existential one. There exists X in S such that, and now when you negate a statement, we saw this with the equations and inequalities where we converted from greater than or equals to less than, or equality from not to not equal. Here we'll just put not Q of X. So that would be the entire negate statement. And in my opinion, this one is just easier to say, easier to write down on paper, flows a little bit faster. Any questions at all, folks, with the negation? Okay, if we were to read it out, we would first think of the quantifier, the domain of discourse as well, and start by saying, there exists a living person. Then you could say for which or such that to kind of verbally flow through where the colon is. I'll go with a such that. Not Q of X. That would be the statement. They are not a full-time student. They are not a full-time student. And then the problem ends right at that step. So this is the practice on just translating ordinary statements from the quantified language into ordinary English. Any questions at all, folks, going in that kind of direction? Okay, I feel like, again, I think I mentioned this already once, but I feel like this direction is kind of the fun one. It makes a lot of sense. We're really just seeing what the quantifiers are, reading them out. And this part right here is really just a redo of what we did in section 3.2 when we introduced the propositions. Only difference now is they're predicates, but we're doing the same kind of work with the logical connectives. But if we go backwards, that's where it gets really challenging, in my opinion. And part of the challenge, I would say, is just the way English language, or really any language, works. There's always a little bit of vagueness in language that makes going from an ordinary statement into a precise, logical, quantified statement a little bit tricky. So that's what we're going to do next. And that's a revision there in red. Again, sorry for forgetting the domain of discourse. I think it's implied, but we need to be specific. I mean, we're just learning this stuff for the first time. So that was the second revision I had to put in these notes. So let's start off by just looking at what we've got here on paper. We have a P of X predicate. I'm going to color code it this way, green and blue. P of X is going to be the statement X is an accountant. Then we have another statement, Q of X. Q of X is going to be the statement X owns a Porsche. The domain of discourse is now going to be all living people. And here's our first challenge. All accountants own Porsches. Let's pause and think about that. We want to write this down symbolically using quantifiers, but we can start by just saying the all there would translate into a universal quantifier for all. We're using the symbol X to denote people, and we're using the domain all living people. So for all X in the set S, we have to put something here to convey what this statement is saying. All accountants own Porsches. Again, let's think about this for a moment. Any volunteers for a suggestion on what we could put down? Yeah, absolutely. Good eye on that. The statement would be not that version of P, but P of X implies Q of X. Absolutely. And let's spend some time with this one to really explain it and think about it. But let me tell you what my brain kind of defaults to, the incorrect answer. It's incorrect to say that this is a statement for all X in S. My brain wants to write down P of X and Q of X. But this one is absolutely false. It just feels right at first, but why is it incorrect? The universal quantifier is extremely strong as a statement. It's now saying every living person is both an accountant and owns a Porsche at the same time, but that's obviously false, right? I'm not an accountant and I certainly don't own a Porsche. This statement is extremely strong, but it's a temptation to put that down on paper. This is a pretty tricky problem. It turns out this is the direction that we would have to go. P of X implies Q of X. But any questions at the moment on why this one would be false? Oh, sorry for covering that up. I want to go back to the implication because, again, this thing is pretty tricky, but let's see if it really makes sense on this statement. It's a statement, all accountants own Porsches, and yet we have an implication there. That's kind of interesting and unique in a way, right? Because this wasn't written down as a P implies Q, if P then Q. None of these showed up whatsoever in the statement, all accountants own Porsches. Yet that is absolutely right. This is one of the tricky ways the implication comes in now that we have a universal quantifier. And let's think through this. Let's see if this statement really fits exactly what we mean in spirit. All accountants own Porsches. If P is true for every single X, that would mean we're talking about the person being an accountant in the first place. Then Q of X would be true here, that would mean they own a Porsche, and the implication works as usual. If we go to say P is true, every person is an accountant, then Q of X, they don't own a Porsche. If that's false, we get a false statement overall. But this is saying for all X and S, if this part is true, P of X, then Q of X must be true. We go to the falses, we get true vacuously. And this is the statement we'd be thinking of when we know we really have an accountant. So all accountants own Porsches really flows through this line. Vacuously true doesn't really imply on this one, because if they are not an accountant, that's okay. The whole statement is still true vacuously. And if Q ever comes out as false, well, that would just mean the quantified state, or excuse me, the implication here would be false outright. So that's, again, pretty tricky as a statement altogether. The all here gave us the universal quantifier and gave us the implication when we went between accountants and owning Porsches. Any last questions or thoughts, folks, getting through this one? Okay, another thought about this one is there's absolutely more than one answer to this kind of problem. You could have said, what about, let me make sure I'm on the right page first. What about this? Some people might not have thought about the implication. Some people might have put this down, not P or Q. And that's a pretty mind-numbing backflips and logic you have to take to think about this one. If you put, for every living person, they are not an accountant or they own a Porsche, that would have been correct as well, because the implication is logically equivalent to this disjunction statement, the one with the or and the negation on P. We could prove that by doing the same thing we did on this problem, truth tables. All truth assignments for P implies Q are identical for not P or Q, but that's just a really hard one to come up with, going from this language here to not pure Q. It works, but I think that's a really, really tricky solution to really think about and come up with. Yet some people have. I've had an exam question that was similar to this one, and people just felt that was what made the most sense, and they were absolutely right. Well, we made a big deal out of part A. Let's now turn the page over to part B. Some accountant, there's another typo. That should be plural. Sorry about that. No, actually, yeah, singular is right. It just tricked my own self. There is some accountant that owns a Porsche. First thing we can do is some is saying there exists, or for some. So we can begin by saying there exists some person who's alive, so someone from the domain, all living people. There is someone such that some accountant owns a Porsche. Let's think about this one as well. Any volunteers for what you would put down on paper for this one? That's kind of a tricky one to think about, right? What's happening here is really it's almost the same statement, right? The only difference is universal quantifier, existential quantifier. But that is a humongous impact on what you write over here. It turns out this one goes like this. There exists a person such that they're an accountant, and we use the conjunction and statement. They own a Porsche, P of X and Q of X. this one is the and statement, and I find it pretty surprising when we first see this kind of stuff. Didn't work over here with the conjunction and statement, but that's because it was a universal quantifier. That's too strong of a statement. It's saying everybody is both an accountant and has keys to a Porsche at the same exact time. But you switch that over to an existential quantifier, this is the right statement. It's just saying there is some person who is at the same time an accountant and happens, oh, that's supposed to be a Q, and happens to own a Porsche. Sorry for that distraction there. So that's the big takeaway on parts, for example, 5. Universal quantifier for a statement like this implies an implication, and an existential quantifier for a statement like this implies the and operator, the conjunction. Well, any questions at all, folks, thinking about these two problems? I think this is probably one of the trickier parts of the note so far. Okay, well, let's move over to the next topics. We're about to finalize the notes and get into the nested quantifiers subject. But first, here is our, as our author calls this, theorems involving quantification. There's lots of stuff going on in this so far. These are statements that are going to always be true through the if and only if operator. And notice that we have lots of stuff that we've been using already. The negation of this statement is the same as this statement over here. We use the triple bars for logical equivalences rather than the if and only if as the author used here, but starts off with De Morgan's laws in the quantified form. Doesn't matter how big the set is. This is a true tautology. It's a tautology through an if and only if. So a different way to say it is you could write logical equivalence in place of the if and only if biconditional. We have vacuous quantification. We really didn't hit this too hard on the notes, but these are statements that are a theorem in the sense that they are always true. Or in other words, these are tautologies. So we have two vacuous types of quantification. They're vacuous because we're talking about all elements coming from an empty set. They're just automatically vacuously true. So they're kind of uninteresting in a way, but vacuous truth does come up like in other situations like subsets. Then we have a whole bunch of other interesting things that we can write down. So this is not necessarily a set of things or tools we're going to be used constantly over and over again, but it's just a nice collection of facts about quantification. And it gets tricky at the very bottom of the page down here, where it's involving just some proposition phi and an existential statement can be just brought into this phi and p of x, which is kind of interesting. But the author includes this language. This is only true if x does not appear as a free variable in phi. I think that should take some time to think about. What do they mean exactly by a free variable? What's being referred to here is, as opposed to the free variable, there's also a bound variable. The x here, as well as here and here, are considered bound because they're bound by the universal and an existential quantifier. When we say a free variable, what we're saying is the statement phi does not depend on x. If phi itself depends on x, and you have a universal or existential quantified statement that also depends on x, and you switch to this statement, we made a pretty interesting kind of logical error. So you do that, and phi does depend on x. The logical error here is called variable capture. It's got kind of a cool sounding name, but that's really just what they're referring to here. X does not appear as a free variable, just means P could be a predicate. It's possibly a proposition, but if it is a predicate, it can't have anything to do with X whatsoever. Well, the major things that we're going to be using is the ones on the top here. But any questions at the moment with anything on this table so far? Okay, well, we've looked at these ideas already, these two on the top. If we negate a universally quantified statement, it turns into an existential statement. We also have to negate the predicate function at the same time. And similarly, if it was an existential, it becomes a universal, negate the predicate function. So we've kind of done this sort of problem already. This is just extra practice on example 6 to round out this section. What we'll do on these is determine the truth value of each statement. After we've done that, we'll negate the statement and express the result using quantifiers. Again, just for the sake of practicing these formulas above once again. So let's take a look at this. This says for all x in the domain R, x squared greater than 0. What would y'all say to that? Does that look true or false? It turns out it's close to true, but there's one small problem with it. There's one way it can come out as false, making the overall statement false on this one. The issue is the inequality here was strict. So if we rewrite a predicate function that goes P of x is the statement x squared bigger than 0, the only way the universal quantified statement is true is if this is true for every possible x. But there's one spot this goes bad. If you plug in a 0, you'd be saying 0 is greater than 0. So we'll say that this one's false because P at 0 outputs a false. We get false here because throwing in 0 into that statement again is the inequality 0 greater than 0. If it had been greater than or equal to, the whole statement would have been true, and we would have put true down here. So we've done the first half. We know the truth value of the entire quantified statement. It's false. And again, that's why the universal quantified statement is so powerful. Only way this is true is if you can prove it's true for every combination of x. Next, we'll negate the statement, and the negation, because we said false here, it must now come out as a true statement overall. So let's put the negation down below. Just to put it down on paper exactly what we're negating, I'm going to write it out this way so the notes look a little bit more readable. We don't not just writing down a statement coming out of nowhere. We're negating for all x in R, x squared greater than 0. This will be logically equivalent to there exists an x in R such that x squared, and this is the next tricky element. Inequalities are kind of finicky when you negate them. Negating means changing the direction. And if this is a strict inequality, we include the possibility of equality as well. So greater than negated becomes less than or equal to. If this was a greater than or equal to, negated would just be strictly less than. So the statement is there exists an element x in the domain R such that x squared is less than or equal to 0. Plugging 0 in there makes the statement true. So the existential statement here is just overall true. I'll say here, even though it wasn't part of the problem, this is true. Well, that's one down. I think this is the last one for the notes before we look into an application problem down below. So this time we were flipping from universal to existential. We're saying there exists an integer this time. Because we said integer, we have to be really mindful about what could go wrong in this problem. Say, for example, if I have a 7 here, then the solution to this. No, I was thinking with an equality rather. If I had a set of integers and I have equality here, but I force the solution to be a non-integer, we have false just because of the domain. But I forgot this one is an inequality. I should have read a little bit further ahead. But keep in mind, we have to be mindful we're just talking about integers this time. It's the statement that says there exists an integer such that 7 times that integer at 5 is less than or equal to 3. So this time the predicate statement is p of x, 7x plus 5, less than or equal to 3. And, well, if we just plug in some values, say you put in a 0 inside there, the output to this is either true or false. But we're saying plug 0 here, we'd get the statement 5 is less than or equal to 3. That would be false. 5 is greater than 3. But that actually doesn't help us out so far. Getting one false on an existential does not tell us if the whole statement is true or false. The only way we can show that this is, say, false is if we go through every integer or prove mathematically that you can never get a true out. So we just try something else. How about, let me backtrack just a little bit. I think my original statement was x. Sorry for that. I was changing gears for a different comment. Should make it look back like what the notes were. So it was just at x plus 5 originally. Sorry for that change and forgetting I made the change. So this time with the original statement, plug in 0, still false. But we're working on the set of integers, so we can just try something else. Say p at, how about -5? If you put in -5 into this predicate, that means -5 goes here, and you get the statement 0 is less than or equal to 3. But that's true. And the moment you've hit true exactly once, you can stop. There's a whole lot of other true statements, but this is enough to tell us that this thing is true altogether. True because p at -5 outputs the Boolean true. We just need one example to show that this is true overall. And if it's a universal, we just need one example to show it's false, but it doesn't work in the other directions. So if this was a true statement, to prove it's true, you would have to show it's true for every single value x. And if this was a false statement, you would have to argue or show that this is false for every single value of x as well. But that's the first part. We've determined the truth of this statement. It is true. You can solve this for an integer in z. Next, we'll negate it using quantifiers, and that statement should come out as false. So here's the negation. It'll be the negation of the entire statement. Exists x in z such that x plus 5 less than or equal to 3. This will be logically equivalent to flip existential into a universal for all x in z. Notice the domain of discourse never changes when we negate the statement. All that changes is the quantifier. We flip it from one to the other. And the predicate, we just directly negate this. Will be the statement x plus 5 is greater than 3. And this is false, only because it's saying for every single possible integer whatsoever, that comes out as true, and it doesn't work for, say, -5. Once again, plug in -5, you would have the statement 0 is greater than 3, and so that whole statement becomes false outright, because one problem that we identified. What we did, folks, that's the major content with quantifiers so far. Any questions or comments at the moment getting through these? Okay, I have one application down below, and the major purpose of that application is to connect the quantifiers and predicates into nested quantifiers, which means now stacking the for alls with the for there exists multiple values just like these before we get to even to the predicate statement. And I felt like a good hook for that would be this problem. This is a problem that comes from calculus, but even if you haven't taken calculus, really it's just a problem involving a graph and a couple predicate statements. It says, suppose f of x is defined when x is near a. So on some open set that contains a, doesn't have to contain, some open set interval that contains a except at a itself, possibly. Hang on, that statement seems weird at the moment. Define when x is near a means that f is defined on some open interval. Let's say here, that should have been around a. Except possibly at a itself. So we could have a graph that goes like this, for example. I have a value a here. We'll put a number here, L, and there could be a problem in the graph, an open hole that comes around like that. And we're just saying the function f has to be defined when x is near a. You can put an open set around a, but a does not have to actually be inside that set itself. So that's a setup so far. Now we're looking at the statement, the limit as x tends towards a of the function f of x, and this is that function, y equals f of x, is equal to L. What that means is, this will be true if we can make the values of f of x arbitrarily close to L. So the function values are going to be these heights of the curve at any point as we're around a. We're saying that this limit is exactly L if f can get as close to L as you would like by taking x to be sufficiently close to a. So x has to be on the left or the right, either side, but it doesn't have to be equal to a itself. It could be, but to this graph, it's impossible. F is undefined at a. When you look at this statement, there are two predicates sitting there. There's this predicate. You're making the function arbitrarily close to a value L. We're going to think of this as P of x overall. By taking x sufficiently close to a, this will be the statement Q, but not equal to a. So what we want to do is quantify this entire statement. But again, this is kind of a hook on why we need nested quantifiers, because there's actually quite a lot going on with this one. Well, let's put this all on paper to show just exactly how it goes. Reading through the statement again, it says, the limit of f of x as x approaches a is equal to that limiting value L, expressed compactly in this way. Let me zoom back in. It kind of broke the notation there. If we can make the values of f of x arbitrarily close to L, that means as close to L as we want. And here's how we can express that. We want to be within this distance of the limiting value L, and we can call this upper value L plus a very small amount. The standard value would use is epsilon. Here, this would be L minus a very small amount, epsilon. So this is being as close to L as we would like for the function value f of x. Well, we'll get within this range, not when we're way out here, because if we're, say, here, we plug a value, we come out, and we're not between L minus epsilon and L plus epsilon. We have to be close to A. So if we're close enough to A, we fall in the right range. We're really close to the limiting value between epsilon, L minus epsilon, L plus epsilon. But that's a whole new statement, so we need a different variable instead of epsilon. To capture on the graph being close to A, we could rewrite another set. This value here on the upper bound could be, say, A plus delta. The value of this here on the lower bound could be A minus delta. And now the statement reads, if we're within this range or round from A, go up, hit the graph, then we're within epsilon distance of L. That would be the limit, but this only works if we can be as arbitrarily close as we would like to the limiting value L. That means this is just one such picture for epsilon, but it has to be allowed to be any epsilon. It has to allow to get smaller and smaller and smaller, never zero, but as close to zero as we'd like. So we have to start with a quantification for arbitrarily close to L by rewriting for all epsilon in the set of non-negative real numbers, r bigger than zero or zero to infinity with a parenthesis on the zero would work. This is saying we are thinking epsilon is really, really small. If I wrote it like this, it would also work by saying just any positive real number whatsoever, any non-negative real number. So that's this part. We can get as close to L as we would like by taking any value of epsilon whatsoever. We're usually thinking very, very small values of epsilon. So that bound around L is just getting tighter and tighter and tighter. But we're only going to get to within L if we're close enough to A down here on the x-axis. That's a whole new quantifier. So for every potential epsilon that you pick, there will exist, now it's a different quantifier, a delta in the set r greater than zero, such that there's a whole new statement we have to write with logical connectives. But this is the statement so far. Being arbitrarily close to L means this must work for every epsilon. But once you pick that epsilon, we have to come up with just one delta that makes us close enough to L. So we have an existential quantifier that comes up next. And now we'll write out the statement. If we're close enough to Q, or excuse me, if we're close enough to A, the Q of X statement, but not equal to A itself, that's just the statement that 0 is less than X minus A, it's within the distance epsilon. When it says not equal to A, that's why we have a greater than, so this is always a positive distance. It has to be within delta, so we're just saying take your X, a distance within delta of A. If that happens, then this will imply the function is going to be close to L. How close? Within the epsilon that we specified, so we'll say that this implies the distance between f of x and L is less than epsilon. So it's a lot going on in this statement. As a graph, this is pretty much the picture, but as a fully quantified statement, this is what it looks like. There are two universal quantifiers, and this is like the trickiest situation whatsoever because that delta depends on epsilon. Delta, that's sigma. Let me try again with my Greek. Delta, that's a funny delta, is a function, a real mathematical function of epsilon. Well, we probably have to work pretty hard to specify how it becomes a function, but it depends on epsilon because if we make this epsilon get closer and closer to L, my bounds on delta aren't going to work. I have to make them closer as well. So there's a dependence relation on the quantifiers as well. So that's what's going on with limits. And it's kind of neat to see it now in the language of quantifiers. Any questions at the moment, folks? Just quantifying the statement altogether. Okay, again, this is not a great homework problem. It's not a problem I'll ask on exams, but it's meant to be a hook on what we're about to do in unit 3.5. 3.5 gets pretty interesting because now we're going to have nested quantifiers just like on this statement here. This was a pretty complicated statement, but writing down anything precisely does have a complicated flair to it if we're using quantifiers. So even though this doesn't seem like it's a big deal, I think it's a tricky problem writing this down using nested quantifiers. And so is this if we're translating it into ordinary language. English language and then negating it. So that's what we're going to be practicing on 3.5. It's kind of a shorter section, but it's just more practice with quantifiers, really, and looking into bigger statements that we could not have discussed in the last section. We're going to go through these notes carefully as usual, and we're going to start quantifying, saying what these definitions really mean in the most precise language possible using all the tools and tricks we have. This requires two quantifiers, so nested quantifiers, just to precisely define a function. We'll do the same for onto. These are pretty tricky problems, so we'll take our time with them. And we'll do one pretty interesting application where we're going to work on a predicate valued function, t of xy. Student X has taken course Y with those specific domains of discourse. C is the set of all courses. S is the set of all students. We'll express this statement in terms of quantifiers and the predicate function t. The more interesting thing that's going to kind of be something we loop back into a lot more starting in chapter 7 is we're going to rewrite this entire statement in terms of for loops using pseudocode. So this is going to be the big project or the big application we'll do to close out our entire section on our entire chapter 3, writing out pseudocode that reflects the nested quantifiers. This is a pretty tricky problem. It will be one similar to this one in the homework, but I think it'll be a lot of fun when you see how it goes. First, let's see if we can get a couple problems down, practicing example 1, and then we'll work our way towards the rest of them when we come back on Tuesday. Any questions or comments before we begin? Okay, well, this is just carryover definitions, just as a reminder. If we write for all x and s, p of x, we mean that this is going to be true if, for every possible x in the domain, the predicate outputs a true. And likewise, the existential statement will be overall true if we find if we find at least one possible element in the domain that gives us a true statement. So example 1 says, write the following statement using quantifiers. The sum of any two positive real numbers is positive. Well, when we say real numbers, we're talking about the domain that we're working with S, so that gets us started. Also, we see that it's talking about, any two real numbers whatsoever. So this would be the universal quantifier. And this one's kind of forgiving. When we did the quantifiers here, the order absolutely matters. You cannot put this first. You've changed the entire statement, and that's kind of shocking in a certain sense. Universal with an existential implies a specific order whenever they're mixed. But this is any two. That means there's two universal quantifiers. It doesn't matter the order that we put these down. I can start with, say, for all x in the set R, let me target that as well. For all x, either write, say, 0 to infinity if you prefer. Our author often goes this way, so I'm just borrowing his notation from the reading of the book. So either way is going to be just fine to write this down. We can say for all x in R bigger than 0, then we move on to the next quantifier. There's two numbers we're working with, so we move on to for all y now in R bigger or equal to 0, or excuse me, bigger than 0. It says positive rather than non-negative. The statement is that the sum is positive. So we'll just go x plus y greater than 0, and that's the predicate in the problem. And again, you can kind of see how the order doesn't matter, right? It wouldn't matter if I put y here and then x. Doesn't matter if you change this y plus x, addition's commutative. And so when it comes to universal quantifiers, you can swap them around. You have the same statement. But whenever they're mixed, we'll see that in the next example. It's kind of like this problem. You cannot change this order. You don't have the definition of the limit any longer. But any questions, folks? Just putting it down on paper. Okay, now we're negating it, but we've been practicing that all along in the last section, 3.4. If you negate a quantified statement, even if there are nested quantifiers, the same rules apply. Both of these are going to flip. If there's an existential here, it would flip as well. So the negated statement will just be, there exists X in the set of positive real numbers. There exists Y in the set of non-negative real numbers. So first part of the negation, just flip the quantifiers. Nothing ever happens with the domain of discourse. So no changing on the inequality there. Then we go such that we also have to negate this statement and go X plus Y less than or equal to 0. Well, we did it, folks. That's nested quantifiers so far. Example 1 is kind of a more gentle tour versus the one we did in 3.4. We'll look into more and more complicated statements as we go. And by the way, this one's a true statement that sum of any two positive numbers is absolutely positive. So this one is true. We're just using properties of the field of real numbers to justify that at this point. But what about this one? This one is saying you found a positive number and another positive number. You added two positive numbers and got negative or 0. That's impossible. You can't even get 0 if one of them is actually positive. So this one is absolutely false. But we should always see that relationship when we go to negate one statement to the other. They should flip. No matter how complicated they look, no matter how many nested quantifiers, one statement is true, its negation must be false. Well, any questions, folks, on getting through that one? Okay, let's try this out again. We have just a few minutes of time, but these don't take too much time. This time we're going backwards. We're going to take this statement here and just rewrite it as a normal, ordinary statement in words. First, let's take a look at what this is saying. It's saying for all real numbers m, let's start there. For any real number, you can mention m if you like. I'll just go with for any real number. There exists another number that's a real number. Let's say there exists sorry, I'm misspelling the word exists. Another real number that's larger than the first. I'll say the first number. Again, if you put m's and n's in that, that would be just fine as well for writing out the statement. I kind of like it read out this way. It's really just the mathematical fact that there is no largest real number whatsoever. You pick any number, and I can find a larger one. It's really complicated as a quantified statement when you really look at it. But again, just going left to right versus saying for any real number whatsoever, we can find there exists another real number that's larger than the first one. And so that's the statement just in ordinary words. It's absolutely true. So when we come back in next class, we'll negate it and see what goes on. But here, another thought before leaving to think about is this y variable does not depend on the x variable whatsoever. There's no dependence relationship. But when you mix these quantifiers, that n variable depends on m absolutely. If m is 10 to the power 50, I'm going to have to come up with 10 to the power 50 plus 1 for an example. And if this is 10 to the power 100, then my old 10 to the power 50 plus 1 doesn't work. I have to come up with a new number to make the statement true. But we'll get back into all those kind of interesting topics that are coming up now that there's nested quantifiers next Tuesday. Any last questions at all, folks, before we call it a day? Okay, well, have a great weekend, folks. I think next lecture will be a blast because now we're looping back into how all this stuff now connects in computer science when we go to write out the pseudocode. We can't run this code because we don't have a database, but in chapter 7, we will be running our pseudocode to test it out. We practice more and more algorithms. But have a great weekend, folks. We'll be back here next Tuesday. Thanks. Have a good one.